Today, we're diving into the world of 7 must-know strategy for scaling your database. But first, let's talk about why and when scaling is necessary. As your application grows, so does the amount of data it handles and the number of users it serves. This increased load can lead to performance issues such as slow response times, timeouts, and even crashes if your database can't keep up. Scaling becomes essential to maintain smooth operations and ensure a good user experience. Imagine you run a startup that's suddenly gone viral. Your user base skyrockets, and your database now needs to manage millions of requests instead of just a few thousand. Without proper scaling, your app could become unstable, driving users away. Or think about a holiday sale on an e-commerce platform like Amazon. The traffic surge during such events requires a scalable database to handle the peak load smoothly. Now let's break down the 7 must-know strategies to scale your database, one by one. First, let's talk about indexing. Indexes are like the index at the back of the book. They help you locate specific information quickly. Without having to scan every page. For example, in a customer database for an online retailer, indexing can quickly find customer orders based on order ID or customer ID. This allows customer service reps to pull up order histories quickly because these fields are indexed. The most common type of index is the B-tree index. B-tree indexes keep data sorted, making them ideal for a wide range of queries. They allow for fast insertions, deletion, and lookup operations. B-tree indexes are particularly effective for range queries, like finding all orders within a specific day range or retrieving customer records alphabetically by last name. Indexes can significantly reduce query execution time. Without proper indexing, even a simple search query could turn into a full table scan, which is extremely time-consuming. However, it's important to note that while indexes improve read performance, they can slow down write operations since the index needs to be updated whenever data is modified. Finding the right balance and knowing which fields to index is key to maintaining optimal database performance. Next, let's dive into materialized views. Think of them as pre-computed snapshots of data that are stored for faster access. They are especially useful for complex queries that would be too slow to compute on the fly every time. A real-world example is in business intelligence platforms like Tableau. Imagine a company needs to generate daily sales reports from a large data set. Instead of querying the raw data every time a report is requested, which could take a long time, a materialized view can store the pre-computed sales data. This allows the report to be generated quickly and efficiently. Materialized views can significantly improve performance by reducing the computational load on your database. However, they must
Scaling up, scaling out, adding read replicas, different read models. Scaling up, scaling out, adding read replicas, different read models, caching, multi-tenant. You have a lot of options. Hey everybody, it's Derek Martin from CodeOpinion.com. So you have a monolith that you need to scale. Now you're thinking moving to microservices specifically for those scaling concerns. But hang on. Here's some things that you can do to scale your existing monolith. You'd be surprised how far you can actually take this. This video is brought to you by Event Store DB, the stream database built from the ground up for event sourcing, CQRS, and event-driven microservices. For more on Event Store DB, check out the link in the description. So when we're talking about scaling, really what we want to do is just do more work. We have more requests, more things that we actually need to process.
It was just a guess. I had no idea where the quote came from.
Why don't I use Lichess? I don't support communism. Bishop 2e4. That's a joke. I know you were gonna type something, YouTube commenters. Relax. Twitch, I know. Twitch gets me. I understand. Twitch. Why don't I use Lichess?
Thanks, Max. Thanks, Max. All right. So my name's Thibaut. I'm a French coder. Been coding for some time. And 8 years ago, I was working as a web developer in a French agency, making websites and experimenting with various technologies. 8 years ago, Ajax was all the rage. Yeah, there's something, if I can show it, maybe. Here it is. That's not easy. All right, chess. Chess is a slow game. It's about thinking for a while on moves, right? So this is a replay, real-time replay of a game that happened recently. The point I want to make is that online chess is a very different beast. It's become like a real-time shooter. It's about mouse skills. It's about predicting the opponent's moves. This is real-time. I mean, I don't know how they do that. I can't do that. They are playing with 15 seconds each on their clock, so it's a 30-second game. There are tournaments of that. There are people playing that for hours without a break. I don't know. I don't know how they do that, but they do it. And every move they play is saved on the database and broadcasted to the other players. So that makes quite a bit of server activity. Is it done yet? Come on, just checkmate him already. All right. Up she goes, and checkmate. There we go. That was not intended. Whoa! There we go. Some numbers. They play up to 1,000 moves per second. They play 1 million games per day. All of them are saved. Each move is saved, and a lot of metadata. And today we have 1 billion chess position indexed in the Opening Explorer, and a bit more than 400 million games in the database. The backend is written in Scala. It's like Haskell, but worse, honestly. But it runs on the JVM, which is a good thing in my opinion. We have like 10 critical servers, plus a lot of artificial intelligence servers playing chess. Data is stored in MongoDB. We can search with Elasticsearch. We use Kyoto Cabinet for the Opening Explorer. And the front end is in TypeScript with Virtual DOM library, SnapDOM. I'm a big believer of functional programming as in immutability, referential transparency, and static typing. What makes us different, it's not the technology or the numbers, is the fact that we have a commercial value of $0. It's quite a UFO in the online chess world because the top 10 chess websites are all owned by companies who have to turn a profit because they have investors, and they rely on paid features and or advertisement. We don't, because as I explained, it started as a programming project, so there was no will to make money out of it, and I never felt the need for it. Also, in my opinion, it's not fun, it's too serious, and I'm not a serious person. So I'm going to talk about what's a free service. Then I'll discuss about the specifics of the online chess communities. And then maybe, if we have time, I'll give a few tips about how to create an online community and make maybe even a free service. So free service has, in my opinion, to be built on free software. It's not required, but in my opinion, it's a solid ground. It's awesome to contribute to free software ecosystem. Everything we write, all the code we have running is open source, usually under the GPL v3 license. It allows a lot of other chess websites to get started with components that we already built. For example, the Agon company, which broadcasted the recent World Chess Championship, used our chessboard open source code to broadcast the games on their website. Another commercial website uses our Stockfish chess engine integration to the browser. And a lot of people are just writing side projects, just like I was 8 years ago about chess, and we're using our code, and that makes me very happy. Also, of course, we get a lot of code reviews.
I interned at two quant firms specializing more in their sort of data.
It is.
So yes,
My friends, let's
to have you with us today. My name is Zvezdana, and I would like to welcome you in front of the whole Joberty team. For those
can't afford.
Let's make a contribution to Lichess and take a look at the new Gitpod configuration. First, we'll click the link that will start a new Gitpod instance, and this creates a remote development environment, and you access it via your browser. So Gitpod is creating a virtual environment. With all of the services necessary to run Lichess, and you'll get an in-browser code editor that you can use too. So you don't need to have anything except a web browser to contribute. Everything will start automatically. This is the terminal where the startup script runs. You get a prompt asking which optional services you want to run. Depending on what you're working on, you just select which ones you want, and it will start up those containers. Now it's cloning the repos and starting the containers. This takes about 10 minutes. Once it's done, as part of the default setup, we get 3 sites available to us. First is our Lichess development site. It has test data in it, so we can log in as one of the test users. Second is MailPit, which intercepts any outbound emails and will show them in this inbox for debugging. And third is Mongo Express, which lets us look into the database in case we need to see schema or data, which can be helpful in debugging. Let's see how we can use this to make a contribution to Lichess. I was reviewing the new user sign-up flow and noticed some things we could probably improve. A new user has to confirm their email address, but when they click the link in the email, there's no confirmation that it worked. So let's see if we can fix that. Back in our code editor, we're going to edit the Leela repo, so open repo/Leela. And to figure out where we need to look, we'll search for the route. And that gives us which controller method it calls. And in that, we see that it calls redirect new user, which is defined right here, and that returns the redirect. Leela has the ability to do flash messages, which add data to the session to appear on the next page load. And some redirects already use that, so let's borrow from those. And we can give it a custom success message. So we modified a backend file, so we have to restart Leela, and let's test it out. This time we'll create a new user, we'll verify our email, and we see the flash message, so it worked. Let's just make sure our code is formatted correctly and ready to submit as a pull request. I'll create a branch for my changes, commit the changes, and then push them to my fork. And finally, I can submit the change as a pull request. I'll add a screenshot so others can see what it does, and maybe this will get accepted into the Lichess codebase.
Microservices. Micro means small, but how small exactly? And service means, well, it does something? It's probably more helpful to understand what microservices are not. A monolith. A traditional architecture where a whole system is built as one unified, self-contained application. It might start small, but over time we add new endpoints and new database tables, and eventually we have one giant code base that does everything. It's very easy for interactions to end up all over the place, and we end up with a big ball of mud. A haphazardly structured, sprawling, sloppy, duct tape and baling wire spaghetti code jungle. The code lacks any structure. Developers have just called any code from anywhere, and over time the system became too complex. So we need some clear structure. We need concepts to live in certain areas of the software and not to leak into others. We divide the large system into smaller, manageable subsystems. We only allow a certain few interactions between boundaries by making some code internal or private, hidden away and inaccessible by the rest of the software. These subsystems are isolated modules all hosted within this large application. This architecture is called the modular monolith. We can get some clean, loosely coupled code that's easy to understand and easy to navigate. We could leave this architecture as it is, or we could host each of these independent modules as totally separate processes. These are microservices. Each service can be updated independently. We can deploy changes to one service while the others continue running. They could each run on different machines, which can scale independently. Performance bottlenecks are easier to identify if we find that, say, one service is using lots of CPU, and if one service fails, the others can still handle requests as normal. Each service uses its own database too, which has similar benefits to the independent services. They can each fail without taking the other databases down, and they can scale independently. Services communicate with each other over a network using some API, whether that's HTTP requests or using a message queue. We need to ensure that we don't deploy breaking changes to an API that is being used by another service, so the boundaries between services become much more difficult to change. Network calls are much slower than the inter-process communication that was allowed before, and it usually involves writing a lot more code to handle the call. All of these constraints can feel like a bad thing, but the benefit is they formalize the boundaries between the systems. Developers are incentivized not to rely on passing information between boundaries too much, and instead build loosely coupled systems that don't depend on each other to function. Choosing the wrong boundaries leads to the worst of both worlds, a distributed ball of mud, where not only do we have spaghetti code, now there's a network involved where everything is slower and more prone to errors. A common mistake is to make the services too small. Nanoservices is a term sometimes used to describe tiny services that only contain one function. This might be an acceptable size for some services, but be careful not to fall into the trap of making services that depend too much on others. Tightly coupled services means multiple services would need changing to achieve most tasks, which defeats the point. So we need to find cohesive groups of functionality that belong together. We can build domain-oriented microservices following DDD to find bounded context for each service, or design services with the organizational structure in mind, so that teams own their services and understand them well and get very good at maintaining them. However you do it, just make sure to avoid that distributed ball of mud.
To have you with us today. My name is Vesna, and I would like to welcome you.
Hello everyone, and welcome to Software Architecture Monday. My name is Mark Richards, and in this lesson number 159, we will continue our journey in architecture styles by taking a look at the modular monolith. You can get a listing of all of the lessons I do on my website at developer2architect.com/lessons. In the prior lesson, we took a look at all this kind of categorization or classification of architecture styles, and we took a look at the layered architecture. Well, in this lesson, we're going to kind of still be within the monolithic architectures, but take a look at the modular monolith. So the modular monolith is basically can be best described as a single deployment unit, which means all of the code is deployed as a single unit of software, but with functionality grouped by domain area. And as you remember from the prior lesson with the layered architecture, that was functionality that was grouped by technical categories. And this we're kind of flipping it 90 degrees and actually grouping things by domain area. For example, maybe this area of a modular monolith contained all of the functionality, including user interface all the way down through persistence for inventory management, for example. Maybe this particular modular module right here is payment and billing domain. And so you can see this kind of grouped by domain area. If we were to take a look at this in the code, what we would find is that in our namespace or package structure or directory, we would find that the highest level node actually describes the domain. Whereas with the layered architecture, we saw that that highest level node, after of course com.myapp.whatever, was the layer, either business, presentation, and then everything following. And so it's a good way of thinking about the modular monolith from kind of an implementation perspective. Now I'm showing the modular monolith here as one code base, but it doesn't have to be that way. Another option within this architecture is to have each of those domains as separate workspaces, even separate Git repositories that are formed into, let's say, jar files, DLLs, packages, or gems. And now during deployment, all of this is brought together to be executed in one deployment unit. And these things could be managed by, let's say, Java Modularity, Jigsaw, Penrose, OSGI, although I hesitate to say that word, Prism and .NET, all of these kind of frameworks as well to help manage the deployment and testing of a modular monolith. And so here, whether it's a jar file, a DLL, or whatever kind of module, would still contain that same kind of domain, inventory, maybe payment right here. So the modular monolith does have, like the layered, some superpowers, and not surprisingly, those really are based on it's a fairly inexpensive architecture. So cost is good. 5 stars is good. Remember, 1 star is not so well supported. And of course, it's simplicity. So this is really good to use if we do have a lot of time and budget constraints, especially during the initial deployment of this. This is a fairly familiar architecture style, and it's fairly simple. There's not a lot of moving parts in it. Another really good use case for when to use the modular monolith is if we have, and also expect, most of our changes being domain-based. I gave an example in the last lesson where we talked about adding an expiration date to our wishlist items. And you saw that that kind of domain change didn't work well in the layered architecture, but here, there's the area of change. And so I know exactly where to go to because this architecture style is delineated by domains. Also, it's good to use also if our teams are also divided into like agile teams or cross-functional teams with specialization. I shouldn't say agile teams because unfortunately I haven't run across some agile teams that are technically oriented. But if our teams are divided into cross-functional teams with specialization, this works well because that domain change can come to a single team and that single team can apply that change. Well, looks like a nice architecture, but there are times to avoid this architecture style. Given that it is a monolith, some of the operational aspects still aren't well supported, but also that agility. Now, you'll notice here, if we start to do a compare and contrast, then in the prior lesson with the layered architecture, these things were only 1 star. We have added an extra star here to say it is a little easier to maintain, assuming most of our changes are from a domain standpoint. So we do have an extra star, but still, if we require that super fast time to market, it's not a very good fit. But also, if we find that most of our changes are technical in nature, and let me give you an example, we continually replace the user interface. Well, what that means is, unfortunately, because that kind of change is technically oriented, this is going to impact every single aspect of this architecture. Or if I replace the database or constant database changes, maybe it's changes to constant business rules. These are kind of things that are more aligned with technical partition as opposed to a domain partitioned architecture such as this one. But also, as you can see from the 1 star ratings, those are times when we have to have really high levels of elasticity, scalability, or even fault tolerance. This is not a good fit. So you can see now the modular monolith and kind of all the summary. It's a very popular architecture style. If you want to learn more about the modular monolith, you can of course go to our book, The Fundamentals of Software Architecture, but also one architect, Simon Brown, who lives in the UK, has a lot of material that he's been focusing on the modular monolith. So this has been...
Hi, friend.
It's Derek.
How do you build
this video work?
How do you build the more
Hi everyone, we are talking about
Hi, it's
In this video, I'll show you how to take a modular monolith and extract one of the modules into a dedicated service. We'll be elevating the logical boundaries between our modules into physical boundaries and moving into a distributed system. We'll have to solve some interesting problems along the way, so let's jump into the code and see what we're going to build. Let me illustrate what our current system looks like. Let's say this is the modular monolith, and inside of it we have our two modules. The first module is called the orders module, and then the second one is called the shipping module. Now these modules respect the boundaries within our modular monolith, and they don't communicate with each other directly. There's no calling to the internal components within a module. Instead, each of the modules exposes a so-called public API. Let me type this out, and this is what we're allowed to call on the other module. So let's say the orders module needs to fetch some information from the shipping module. It's going to send a call to the respective public API of the shipping module. The public API is going to delegate this into the internal implementation, and then we get the response back. The same goes if we want to get something from the shipping module, we reach out to the public API of the orders module, which is going to delegate this call to the internal implementation. And this all works fine while we are still in the module monolith, because the boundaries that we have here are purely logical. But what's going to happen if we decide to elevate these boundaries into physical boundaries and we move from a monolith into a distributed system? So let's say now our boundaries become something like this, where we have two dedicated components, and you can see that our communication doesn't change. We are still reaching out to the public API of the respective modules, and if you implement this correctly, all that should change is the technology that we're using for communication. So in case of our monolith, the communication is going to be using method calls. Our two modules are in the same application, so using method calls is fine, but when we move into a distributed system, then method calls will no longer work, and we have to resort to network calls using HTTP.
You want modules, not microservices. For those that are watching this on YouTube, if you're wondering why chats like this.
How do
Sabina Hossenfelder is a part-time science YouTuber, part-time physicist, prolific author, and fabulous dancer.
It's taken me some time because my
one thing?
Ooh. Too many microservices.
Too many microservices. I'm from the old school, so I've suffered through monoliths. I'd rather suffer through the microservices.
I thought you said these questions weren't going to be hard. I'm going to say monolith. It'll be easier to maintain.
Okay.
But still awful.
I know a little bit about microservices, so I'll go with microservice.
I feel like a monolith would be like better. I don't know, like when you have like too many microservices, it's like too much.
Microservices all the way.
Ooh. Too many microservices.
Too many microservices. I'm from the old school, so I've suffered through monoliths. I'd rather suffer through the microservices.
I thought you said these questions weren't going to be hard.
How do
I've worked
Hey folks, Serdar here. In this episode of Dev with Serdar, we're going to look at the structure of a modern Python project, how to lay out the files in the directory, what the most important pieces are, and how to keep things organized going forward. New Python projects should, whenever possible, be laid out according to the guidelines listed by the Python Packaging Authority. Even if you don't plan on distributing your project, this is still a good idea, because it gives you a set of standards for how things behave and where people expect things to be found. To understand better, let's look at an actual project. This is a project that I've shown here from time to time in different incarnations. It's my implementation of Conway's Game of Life in Python. The first thing you'll ask is, where do I put my actual code? All your project code goes in a subdirectory named source, src. You can place your code directly in source, or you can subdivide it into other directories for the sake of namespacing parts of the project. For this one, I have the core of my project under Conway, that's the main namespace, and another piece of it in render. That's a component written in Python and compiled to C. I do recommend using at least one namespace directory as it makes organization easier. Next, we have files in the root of the repository. For Python projects, the common and most important thing to have here is the pyproject.toml file. That's the file format that's now used to store Python-specific metadata about a project. Don't be intimidated by all the things you see in this example. If you're just getting the project going, these lines here at the top are the only ones you really need. The project section declaration, the name, which is the name that's listed for your project when you use pip install to install it, the version number, and the dependencies, if there are any. Everything else can be ignored for now. There's a link down in the description for the video about where to learn more about what goes into a pyproject.toml file. Another thing that does appear in the root of a Python project is setup.py. Most of what's now in pyproject.toml used to live in setup.py, not all of it. Setup.py is run when your program is installed with pip, and it contains actual Python code instead of just data to do things that cannot be expressed in pyproject.toml alone. For instance, in this project, it's used to compile that C extension module written in Python. So while setup.py is not mandatory, it's there for projects that need it, and some projects really do need it. So the next set of items after this, these are optional but common. First is your git ignore file, used to keep some files out from being checked into version control. You generally do not want to check in your virtual environment. You don't want to check in any PyCache directories or any egginfo files. Those are generated by pip install. I have a few other file types and directories listed here, but those are specific to this project, and these three types are really the things that you need to keep out of version control. Next is any documentation that goes with the project. In this case, all I have is a simple README file in Markdown format. If you have documentation that's auto-generated,
Hey friends, welcome back to the channel. So
a software company like Google maintains a lot of code. Like seriously, a lot. Like over 2 billion lines of code and nearly 100 terabytes of data to go along with it. It's a scale that's hard to even comprehend. Like all the stars in the universe, where all the universe is in the multiverse, and you have thousands of engineers around the world working on it simultaneously. But get this, they store all their code in a single monolithic repository, and they've been doing it since the very beginning. Today, Google's monorepo is likely the largest code base in the world, but it takes an extraordinary effort to scale. They have their own homegrown version control system and a highly advanced build tool called Bazel, which goes by the much cooler name of Blaze. Extraordinary effort to scale. They have their own homegrown version control system and a highly advanced build tool called Bazel, which goes by the much cooler name of Blaze internally. In today's video, you'll learn everything you ever wanted to know about monorepos and how you, the humble JavaScript developer, can build a high-performance monorepo in your garage. If you're new here, like and subscribe. We're so close to 1 million, and if you hit the button right now, we might even make it there by Christmas. You may have heard some exciting news last week that Vercel acquired a company called TurboRepo. It's a build tool written in Go that makes it really easy to manage multiple apps and packages in a single Git repository. But first, let's answer the question of why would I want to use a monorepo? There are many reasons, but at the highest level, it gives you visibility of your company's entire codebase without the need to track down and clone a bunch of different repos. In addition, it provides consistency because you can share things like your ESLint config, a UI library of web components for your design system, utility libraries, documentation, and so on. The real power, though, comes in the form of dependency management. Imagine somebody makes a breaking change to a shared library. All affected applications will know instantly, and monorepo tools can actually help you visualize the entire dependency graph of your software. When it comes to third-party dependencies, a monorepo can dedupe packages that are used in multiple apps. A monorepo is also ideal for continuous integration and automation because your code is already unified by default, making it much easier to build and test everything together. But there is one big problem with monorepos, and that's the fact that they're big. As the monorepo becomes larger, there are more things to test, more things to build, and a lot more artifacts to store as a result. VS Code will lag trying to process the massive Git history, and you'll need a 20-minute smoke break waiting for everything to run on the CI server after every commit. To operate a monorepo at scale, it's absolutely essential to have the right tooling. That's why Facebook created Buck, Microsoft created Rush, and Google created Bazel. You just need a PhD in order to use it. Luckily, there are other options out there. The most basic approach is to use your package manager like Yarn or NPM to define workspaces. These tools basically configure your project with a root level package JSON, which then has nested workspaces like apps and packages that are linked back to the root level project. A cool thing about this is that it will dedupe your node modules, which means if you have the same package installed in multiple apps, it will only be installed once. It also allows you to orchestrate scripts, like if you want to build or test all of your apps at the same time. That's a good, easy place to start. But if you're building an open source project that publishes a bunch of different packages, then you'll likely want to look into a tool called Lerna, which is a tool that can optimize the workflow of a multi-package repo. Here's an example. Turf.js is a geospatial library that has a ton of different packages that are essentially helper functions for working with geolocation data. Each one of them can be installed as its own package and lives in its own subdirectory here in the repo. Lerna is the tool that it uses to help manage this workflow efficiently. Most importantly, it allows you to publish all of your packages to npm with a single command. These tools are great at configuring monorepos, but they still suffer from the same problem I mentioned earlier. They become really slow and difficult to work with as they grow larger. One problem is the installation of dependencies. If you're looking to improve your install speed, an easy optimization to make is to replace npm with pnpm. It's a drop-in replacement that will install your dependencies globally and symlink them, and that can make your install speeds up to 3 times faster. That's a nice upgrade, but what really makes a monorepo slow is the constant need to recompile, rebuild, and retest everything. And that brings us to the fun part of the video, where we talk about an entirely different class of tools that can make your monorepo operate at the speed of Google. The tools I'll be comparing are NX and TurboRepo. They both operate as what I would describe as a smart build system. What I mean by that is they create a dependency tree between all of your apps and packages, which allows the tooling to understand what needs to be tested and what needs to be rebuilt whenever there's a change to the codebase. They cache any files or artifacts that have already been built and can also run jobs in parallel to execute everything much faster. We'll look at some example code in just a second, but first, what is the difference between NX and TurboRepo? NX has been around from a technical standpoint, and now it's time for some packages, where apps are the actual app.
You want modules?
Welcome you in front of the whole Jobberty team. For those who maybe don't know who we are a developers community with more than 70,000 users and a place where you can explore IT companies, IT jobs, and read experiences from your colleagues from the industry. We are currently present in 6 markets: Serbia, Croatia, Romania, Bulgaria, Macedonia, and Slovenia. And we strongly believe that sharing is caring, and that is why we have started this series of free webinars with industry experts. This is our 8th webinar, and today we are going to be talking about modular monoliths. We are happy to welcome Milan. Milan, welcome. welcome and thank you for being here.
for
Milan
inviting
is Milan is a software architect and tech YouTuber, and he will be sharing with us some tips and tricks on how to build a modular monolith. And lessons that he has learned along the way. And one more thing, we're going to be having a QA session on the end of the webinar, so please feel free to ask any questions that you maybe have for Milan or for us in the QA section. I don't want to be wasting our precious time any longer, so Milan, the floor is all yours.
Thank you for the delightful introduction. And thank you to Joberty for extending this invitation to me. It's an honor to be talking to you today. My name is Milan. I'm a software architect by day and content creator in my spare time. Although you could argue that creating content is my primary occupation, given how much I share daily on the various social medias that I'm present on. You can find me on YouTube, LinkedIn, Twitter, and on my website where I write a weekly blog. You can see all the links on the screen. And without further ado, I'm going to jump into what you all came here for today, which is modular monoliths. I'm going to talk about my experience using this architecture on a real project for the past 2 years. I'm going to explain as best as I can how you can build a modular monolith and what are some of the lessons that we learned along the way. Unfortunately, we had to learn those lessons the hard way, but I'm hoping that in sharing my experience today, you're going to be able to learn those lessons right away and you won't make the same mistakes that we did. So what is our agenda for today? We're going to briefly talk about the monolith architecture. Then we're going to jump into microservices, just on a high level. I'm also going to do a comparison between monoliths and microservices. And then we're going to do a deep dive into modular monoliths. I'm going to explain what this architecture is, how you can build one, what are the challenges of actually building a proper modular monolith, and what are some of the lessons that I learned along the way. So here you can see the monolith. What we mean when we say monolith architecture is we have just one application representing the system. Typically, it's going to be one solution if you are working in a .NET environment, so that one solution with one executable represents the monolith. And these days, it's considered kind of old-fashioned. Everybody wants to be working in some other kind of architecture because it looks cool on CVs, among other things. But I think there is a lot of beauty in creating a good, solid monolith, which is why I'm trying to talk about modular monoliths, which are, in my opinion, a good way to build monoliths. And one of the issues with monoliths and why people moved away from them is limited scalability. And what I mean by this is you only have one application, one system. And if you want to scale something, you only can scale that system. I'm going to talk about this more in just a moment. On the other end of the spectrum, we have microservices. So here's our representation of a very complicated system where each node on the screen is one microservice. And I'm sure there are actually real world systems that look a lot like this. And if you're working in a system like this, I am sure you're having a lot of fun. So when we say microservices, we mean that many individual services, each doing their own job, form the whole larger system. These days, it's considered cutting edge and cool. Everybody wants to be working with microservices because they are very popular, mainly because it's challenging to work with them, but it's also fun and exciting. And one strong advantage of microservices is that, at least in theory, they are infinitely scalable, because whenever you want to scale something, you can scale that service either vertically or horizontally. Or if you have a bottleneck, you can extract it into a separate service and then scale that independently. So let's try to compare monoliths and microservices on a few points. The first is in terms of deployment. For monoliths, we have one deployment artifact, whereas for microservices, we have many. Or rather, for each service that is part of our microservice system, we have a deployment artifact. And for microservices, you're going to find that deployment is generally a lot more complicated and a lot more things can go wrong than with monoliths. When it comes to communication, in a monolith, typically components talk to each other by simple method calls. Given the nature of the system is everything is in one physical application. And with microservices, it's a little bit different because each of your service is an independent application running in its own server. So your services, if they want to talk to each other, they have to resort to using network calls, typically using HTTP, but there are other approaches, like messaging, for example. Now, when it comes to scalability, monoliths are usually vertically scalable very easily. You can always beef up that server where your monolith is running, make it a bigger machine. And you can horizontally scale a monolith, but the downside is you're scaling the entire application and not necessarily the bottleneck that is probably causing you trouble. Where with microservices, you have the freedom to scale both horizontally and vertically, and even extract services from your existing services if you need to scale some part of your system further. When it comes to databases, in a monolith system, you will typically only have one database, which is very easy to work with. And with microservices, you have usually one database per service, but your entire system is comprised of many individual databases, which adds another layer of complexity. Transactions are available almost out of the box with monoliths because you're usually working with just one database, so you are transactional by the nature of the system. And with microservices, it becomes very interesting because if you want to enforce consistency among services, you have to resort to using distributed transactions, which they slow performance and they introduce a lot of complexity the more services you're trying to keep consistent, which is why people typically tend to trade off consistency and embrace eventual consistency, where you commit a transaction inside of a single service, which is transactional or consistent, and then you somehow notify the other services in your system of the change that happened, and eventually your system converges to a consistent state. And when it comes to scaling teams, again, we have kind of opposing points. With a monolith, it becomes difficult to scale with a large team because everybody is working in the same code base. There are a lot of conflicts, a lot of teams making changes to potentially the same parts of code, and it's kind of messy to work with. With microservices, you can make sure the service is large enough to fill the needs of your team and not small enough so that nobody has enough work to do. So it's very easy to scale microservices with large teams where each team can be responsible for one or more services depending on how big your services are. So I have a quote here from a guy named Martin Fowler. You might have heard of him. He's actually very influential in our industry, and he said, you shouldn't start a new project with microservices even if you're sure your application will be big enough to make it work flat. Now, I'm going to give you a moment to ponder on this quote and try to think of what he actually tried to tell us when he said this. So, in my eyes, the reason you shouldn't be starting a project with microservices is because you are going to have a tendency to make your system very granular. You're going to want to make microservice for this and microservice for that, and before you know it, you have dozens of microservices, whereas if you started with a monolith application and then worked with that for as long as you could have, and the benefit of that is you're going to naturally see where the bottlenecks are in your system. And when bottlenecks start appearing in your system, that's a very good sign that that part of your system can be scaled out into a separate service, so it's kind of a more natural evolution towards microservices. But again, if you build a monolith the traditional way, moving into microservices becomes a little bit difficult. So what if we could have the best of both worlds? If we could get the physical architecture of a monolith, where everything is still inside of one system and one physical application, one deployment. architect, and on the other hand, we have a logical architecture of microservices where individual features of the system are kind of naturally grouped together as they would be inside of a microservice. And another benefit is to have the ability to move to a microservice architecture easily. So we can achieve this, and it is called a modular monolith. So I'm going to try to explain now what a modular monolith is, and I'm going to start by sharing a few definitions of the modular monolith with you. So the first definition says, a modular monolith is a software design approach in which a monolith is designed with an emphasis on interchangeable and potentially reusable modules. So this is kind of a long definition, but the highlight is interchangeable and reusable modules. Okay, let's see another definition. So a modular monolith is an explicit name for a monolith system designed in a modular way. So we can see that kind of everything revolves around the word modular, and the definition of the word modular is consisting of separate parts that, when combined, form a complete whole. I'm not going to read the rest of the definition, but the main point here is you have distinct parts in your system that are kind of independent on their own, but together, when they come together, they form a complete system. in our world, this is going to be an application. So everything is easier to visualize with a diagram. So I prepared a monolith diagram here of a sample eShop application or e-commerce application, if you will. And I did actually work on a similar system for the previous 2 years, so I'm using that as an inspiration. So if it were a monolith, a typical monolith architecture, you would have one application. For example, it can be on ASP.NET 4 by API. And all of the components in our system are going to be C# class libraries, for example. And we have just one database in the system. Now, if we were to convert this system into microservices, we could end up with something like this. So here you can see 4 separate microservices. We have the catalog service, which is responsible for telling us what products are available in our system to be bought. Then we have the order service, which is responsible for creating, managing orders, shipping them, taking care of payments and so on. We have the customer service, which takes care of the users in the system, which are rather the customers. And then the collaboration service, which exists so that customers can interact with sales representatives to create an order, because in this system, creating an order is very complicated. It's kind of a custom-made e-commerce application. So you can see kind of the contrast with these two systems. On the one hand, everything is monolithic together. On the other hand, everything is kind of nicely organized into individual services where each of them provides its own functionalities. So if we were to try to combine these two diagrams into one, where we want to achieve the physical architecture of a monolith so that we have one system, and yet we want to keep this logical separation that we have with microservices, we would end up with something like this. So this is how a modular monolith would look like. Each of your services would now become a module inside of your modular monolith. But at the end of the day, this is still just one monolithic application. It's one physical application, and all of your components or modules inside of the system. System are interacting with the same database. Now, I want to highlight here that there are explicit boundaries around the modules, and the arrows here are actually all pointing to the database. They don't represent interaction between modules, although I will talk about that in a moment. So, let's talk about what are the challenges of building a modular monolith. And as I walk you through the challenges, it's going to become a lot clearer how you actually should build a modular monolith. So the first challenge is actually identifying and defining your modules and bounded context. The second challenge is solving communication between modules. You'll see that there are multiple approaches to solve this. And the third challenge is solving module data independence and isolation. I'll talk about this in depth in the last part. So let's start with defining modules and bounded contexts. So what modules actually are supposed to represent are cohesive sets of functionalities, where cohesive means something that naturally fits together. So if you recall from our previous example, we had a couple modules. For example, probably something that you can easily relate to is orders. So everything around the orders functionality will naturally flow together into a cohesive set of functionalities. We also call this a module. On the other hand, we have a catalog module, which covers everything related to representing line items and other things that are available inside of the eShop application. So one definition of what a module can be is the term bounded context, which comes from the book Domain-Driven Design, which was written by Eric Evans. I recommend everyone should read this book, even if you may not like the ideas represented in the book and you don't want to use them in your code, that's perfectly fine. But I think you're going to be
welcome you in front of the whole Jobberty team.
Mainly because it's challenging to work with them, but it's also fun and exciting. And one strong advantage, but the main point here is you have distinct parts in your system that are kind of independent on their own, but together, when they come together, they form a complete system. We work on systems, and as I even if you may not like
when you are developing multiple
I will be talking about my AI learning journey. This is a topic that I chose deliberately with a somewhat broad title because, you know, you have to plan these things in advance, and I really didn't know what I would want to talk about on this topic by this time.
Like the ideas represented in the book and you don't want to use them in your code, that's perfectly fine. But I think you're going to be a better engineer after reading this book because some ideas presented in the book are very, very good. One of those ideas is a bounded context, and what a bounded context means is it represents a boundary within a domain where a particular domain model applies. So again, I'm coming back to the definition of modules where I highlighted that they kind of represent a boundary around a set of functionalities, which also aligns with bounded context. And an interesting thing with bounded context is that a single entity, or you can envision it as a table in the database, can belong to more than one bounded context. An example of that can be a user. A user represents different things in the bounded context of an order, and different thing in the bounded context of a payment, and different thing in the bounded context of a shipment, for example, but it's still the same physical entity. So one way also to envision modules is that each module can be treated as a separate application. This also has implications in how you define a module in your actual code, which I'm going to talk about now. And I want to discuss how do you actually architect an individual module. Once you have figured out what are these features that you believe belong to this module, what do you do next? So I said that you can envision a module as a separate application, which means that you need to apply some sort of architecture to your module. And you're going to have many modules potentially inside of your module monolith. One example architecture that you can apply is the layer architecture, which is very standard. You have just 3 layers, one for your user interface, which in our case is probably going to be an API. Then you have one layer for your business logic and one more layer for the database. Another option for how you can architect a module is using the Plane architecture. If you're following me on social media, you'll probably know that I'm a big fan of the Plane architecture. This is because I've used it extensively on many projects, and I have found it to be very good for solving many problems. With the Plane architecture, you can represent your layers of your domain, and when comprised together, all of the layers represent one module, and you can have more than one individual modules. And lastly, one architecture that has been gaining a lot of popularity recently is the vertical slice architecture, where you have a vertical slice spanning all of the, for example, here layers of the layer architecture, but kind of all of them are physically placed together, so that it's easier to navigate individual features. So it doesn't matter really which architecture you choose for your modules. You even have the freedom to choose different architectures for different modules. But what I want you to take out of this is that one module should be architected like an individual application, even though it's part of your monolith. If you want to see a good example of what a modular monolith looks like, here's a link to a repository on GitHub, which contains an example of a modular monolith with domain-driven design. I personally used this repository during my research of modular monoliths, and I found it very, very nice to kind of see what the concept is, and then try to kind of expand it with my own ideas. Thank you very much for sharing the link in the chat. So moving on, let's talk about communication between modules. So every module is going to expose some sort of public API that other modules can call. This public API can be maybe an interface that other modules can call to interact with that module that is exposing the public API, or it can be something else. I'm going to talk about that in just a moment. Now, it's important that there are no references allowed to other modules in the system except the public API. So if we have two modules, let's for example say that they're architected using the vertical slice architecture, they are only allowed to call the public APIs that they expose, and they cannot reference anything else inside of other modules. Now, how you achieve this is you hide implementation details of your modules internally. In C# you can achieve this using the internal keyword, which helps you hide the given class that is decorated with this keyword inside of that project. So this is how you can achieve kind of implementation hiding between modules and only expose a public API that other modules can call. Now, when it comes to actually implementing this, you have two approaches. One approach is using method calls. So let's say the catalog module is exposing a public API, and the order module is interested in calling that API. This is going to be an interface for the catalog module, and also the implementation is going to reside there. But the order module will be allowed to reference this interface, and at runtime is going to be provided the actual implementation. So the benefit of this approach is it's really fast because you're relying on in-memory calls, which are both reliable and performant. You can only call the public API of other modules. And the problem is, and potential pain point, that this introduces runtime coupling. So you are calling the public interface of another module, but at runtime, an interface can be instantiated. So if you're using the interface, something has to implement that interface and actually run that code. So you're introducing coupling at runtime, which may not be apparent, but it's something you have to consider. And that is because if you ever wanted to extract individual modules into separate services, so now you're moving from a modular monolith into a microservice system, and you were using method calls, your implementation would break because now your other module, for example, let's say the catalog module here, if it were a separate application, then those are different memories, and you can't execute memory calls. So you would have to re-implement that public interface, probably using HTTP calls over the network to be able to talk to other modules. So now you switched runtime coupling for strong coupling over HTTP. So because of this, there's a different approach, which I'm more a fan of than the previous one, and this is module communication using messaging. So the benefit of this approach is that it is asynchronous. If modules want to interact with each other, they send messages over a message bus. It is also possible to implement RPC-like calls over a message bus. So if you're familiar with a library that is called Mass Transit, it implements this send a request-response communication model, where let's say the order module wants to request something from the catalog module. It would send a message to the queue. The catalog module would receive this message, handle it, and then send a message back, which will go back to the order module. Now, of course, this abstracts away some important implementation details, like which queues are being used, and also you need some sort of correlation ID between messages so that you know what message you are waiting back. But if you don't want to deal with these complexities, the Mass Transit library implements this very nicely. So how you interact between modules using messaging is you define contracts or interfaces for your messages, and you can share these contracts using maybe a NuGet package or a shared library where either all your contracts for a single module reside, or you can even share all of the contracts for the entire application and kind of manage them all in one place. So the benefit of communication like this is that it is decoupled. If you do a thought experiment, let's say we want to again pull out the catalog module into a separate service. If we were using a message bus and everything was going over the bus by sending messages, everything will still function the same because we are not relying on in-memory call to implement communication. We are using an external system which still exists even if we were to go from a modular monolith into microservices. So this is one very big advantage of this approach. Of course, the downside is that you do get reduced performance if you rely on too much messaging. So you're making a trade-off. If you expect that your modular monolith is realistically going to move into microservices, maybe you're better off using this approach from the start of your project. And again, the benefit is it's easy to extract modules into separate services. So this is kind of the high level of how you communicate between your modules. You can either use in-memory method calls, or you can use messaging over a message bus. For example, we use the RabbitMQ. Now, another important thing that you need to consider, apart from messaging, is the independence of data between modules. So every module is responsible for its own data. So this is a constraint that you have to impose on the system, because if you break this and you allow sharing of data between your modules, then you're going to end up with a mess. So another rule that you have to enforce in your application is that querying data directly from different modules in the system is not allowed, which comes hand in hand with the fact that every module needs to be responsible for its own data. And to achieve this, you have different levels of data isolation that you can resort to. And I'm going to talk about these data isolation levels right now. But again, I want to stress and highlight this again. Every module in your system has to be responsible for its own data, and there is no querying of data from other modules. So you can't directly access the database of other modules. So let's talk about how we can isolate data between modules. So there are 4 levels, and the first level is no isolation. So everything is in one physical database, and there is no isolation between modules. And this is the worst approach possible, and definitely the one that you should not even consider. So here the problem is you're probably using foreign keys between tables in different modules, which introduces coupling. So if you try to extract these tables, you will run into a problem because your foreign keys will now break and so on. So one level up in terms of isolation is still using the same database, but using a different schema per module. So now you're still in the same database, but you're achieving at least logical separation of tables inside of the database. So in the example here, each of the modules from our example architecture has its own schema. And another thing that you want to impose here is to not use foreign keys, even though you can, because this is going to make it easier for you to migrate into more constricted levels of data isolation. And again, each module can only query the tables from its own schema. So no querying between schemas. That's very important to have a proper modular model. Now, the next level of isolation, if separate schemas are not enough, is using different physical databases. So let's say we're still using SQL, but each of our modules has its own database. Now, this can all be on the same database server, but at least it's a separate, physically isolated database, so you can really easily query between the databases without introducing a distributed transaction, and you don't want to go there. So this is probably something that you may want to consider, either this approach or this approach if you were to start out. And then there is one more level, which is kind of exotic, but if you need this kind of isolation, it's very interesting, and that is now you have different databases for each module, but you're also using different database type or database management system. So let's say for the order module, we want that relational guarantees and joins, so we opted for a SQL database. Now for the catalog module, where we are dealing with products and product information and a lot of unstructured data, we want to use maybe a document database. For the customers module, where we have a lot of relationships between customers, we opted for a graph database. And for collaboration, for some reason, just to make this slide look better probably, we used a column store database. So you can even do something like this, where you have both physically separate databases between modules and also an entirely different database type, which fits the needs of that module. So you have a lot of freedom when it comes to how much isolation you want to impose on your database. A good start, again, is probably using either the same database and a different schema per module, or using different databases, but still using the same database type. For example, all your databases are PostgreSQL. And this more or less wraps up the story of how you can build a modular monolith. And I want to share with you a few lessons, a few hardships that we encountered in the previous 2 years while working on this architecture, so that you don't have to make the same mistakes that we did. So the first lesson or learning that I would like to share is you should spend more time defining module boundaries, and I promise it's going to pay dividends later. This is because when you're first starting out, it really isn't apparent how your system is going to evolve. So if you spend a considerable amount of time at the beginning of the project just thinking how your system is going to grow, what are the parts of the system that kind of we may want to make independent in the future, you're going to end up with a lot better defined modules, and this is going to allow you to both develop your system faster and kind of later scale it out in a much more performant way. So the next thing is about eventual consistency, and eventual consistency is great. You can achieve it in a modular system, in a modular monolith system. You should definitely use it, but you need to plan for it. So one issue that we ran into was we designed all of our modules to be independent, and they were communicating by using messages over a server bus. And we kind of implemented the entire system to be eventually consistent, and we ran into an issue where kind of the eventual consistency came back to bite us. So you have to consider how eventual consistency is going to reflect on your user experience, and maybe where you don't have the luxury of using eventual consistency, because some changes in your data may be slow to reflect on the user interface, and this is going to lead to bad user experience. Now, there are ways to go around this. For example, your user interface can do eager updates, kind of behave like the update is already applied in the database, and wait for the
We developers often model systems with entities and their relationships. This works great for small systems, but as they grow and entity relationships get more complex, it's easy for a system to get messy and difficult to understand. We want our models to be simple and concise, but the real world doesn't have one simple, unified model for everything. Naturally, the language we speak assumes a lot of context. Let's say you have a support or a help system on your website. A customer might raise a ticket and then they find they need to log into their account. But what if your business is a train booking system? Whilst you still have this support page, customers wanting to catch a train want to buy a ticket with money from their account. Or, even more complicated, passengers are directed to an area called a platform, which is how we split the station into several numbered areas. But some staff, such as maintenance, will further subdivide those areas into spaces such as the shops, cafes, and then the area where the passengers stand, the platform? There might even be a single platform that spreads across many platforms. See, in spoken language, we would automatically understand what these words mean by the context they're used in, but in code, these complexities can make a system quite difficult to work with. We can make our programming language work like our spoken language by separating code into these contexts. We define areas where the code can use a different model to solve different problems. This is called a bounded context. It's a part of the software where particular terms, rules, and definitions apply consistently. So when we're in one bit of the system, the platform refers to one thing, and when we're in another bit, the platform means a slightly different thing. Sometimes the same object exists in multiple models, but with different properties to interact with. And sometimes the same object exists, but it's referred to by a different term. Working out where to draw these boundaries in a software solution can be very difficult. One technique is to draw a context map, showing the language used around an organization, and then find subdomains like these, and separate out a bounded context for each subdomain. There are a few different types of subdomains. A core domain is what makes the organization special. It's a bit that gives you a competitive advantage. Whilst being perhaps a small amount of the overall system, this is where the vast majority of your business efforts should go. Areas that aren't quite that unique special ingredient to the business but still require some specialized skills are called supporting subdomains. Maybe we can outsource these or at least put less effort into them. Then there are areas that many other businesses are doing as well. For example, those support tickets from earlier, or invoicing or email marketing. These are called generic subdomains. For these areas, we can most likely just purchase third-party off-the-shelf tools. Those third-party tools will use their own model and language. This is a great example of a bounded context. Our colleagues that work with these tools daily may even use this language when discussing problems in their area. For example, the marketing department might call it an email campaign because that's what the third-party email service calls it. In this case, when we integrate with this other context, we might just want to conform to that model and use its language whenever we need to talk about a relationship to these solutions in a different context. But there might be other bounded contexts that we don't want polluting our system.
But we have all these thousands. thousands of people involved. Okay,